Hi student and audience. Last week we skipped one lecture, so maybe it's better to review the past lecture, lecture 11. So this is the cover page of lecture 11. In the lecture 11, we discussed the design examples of new design approach. You understand there are two different approach. One is the new approach and the other one is classical approach. Apparently they are very different. In the new approach, we have include the sampling effect of the current mode control, and the sampling effect is smeared in the power stage dynamics converter, and it emerged as the second order transfer function in the control to output transfer function. That is, of course, that is reflect to the loop gain. So in the loop gain, we have double pole at the half the switching frequency, and the double pole is creating the peaking. If peaking, the peak value of the peaking exceed the 0 dB line, so we will be in trouble because of the Nyquist criterion. Maybe converter becomes unstable. So that was the summary of new design approach. So Ridley recommended the QP is some number between 0.2 and 1.2. Okay, this range is somewhat arbitrary, so but not very small number and very big number should be avoided. Okay, so maybe QP of 1 is most common. So QP is 1, there is no peaking. Double pole is there, but you cannot observe the peaking. Okay, so we applied the new design approach to the buck converter, and we performed the control design and evaluate the closed performance of buck converter, and we compared with the classical design approach and the new design approach. Okay, so classical design approach is very different from this one. So we didn't include the sampling effect. So there is no QP or no double pole at the half the switching frequency. So everything is very peaceful, but the loop gain crossover frequency should be placed somewhere between 10% to 30% of the switching frequency. That was my suggestion. Okay, and we observed somehow they are related. Okay, so we'll discuss this in the next lecture slide. And we move to forward converter. We repeat same thing: control design, performance evaluation, and comparison with classical design approach. So this slide explains the details about the current loop design. So first step is this one: this RI, current sensing network gain, should be selected. Okay, this is related with the maximum value of inductor current, sense the inductor current, and the maximum value of this voltage accommodated to the input port of PWM chip. Okay, so this is nothing. This is just some not arbitrary. This selection of this is very trivial. Then this one QP we select as 1. This is the expression of the QP. So SE appears here. So by controlling this SE, you can adjust the QP for the desired value. And the QP is 1 is most common design practice. Okay, so this is the new design approach. But if you compare this thing with classical design approach, this is the same as selecting the current loop crossover frequency at the half the switching frequency. So there is a relationship between this, and we will prove this today. Okay, and following this, and this is the slope of compensation lamp, and this is the peak value of this compensation lamp, and MC is some parameter defined in this manner: SE divided by SN. If this MC is closer to this unity, then means there's a strong current mode control feature in this control scheme. This is the current mode control scheme, but we are thinking as the current mode controller is some combination of purely current mode control and voltage mode control. Okay, so the effect will be mixed here depending on the ratio of this. This is slope of compensation lamp, and this is slope of sensed inductor current. Okay, and finally we compared with that the new design with classical design. Classical design, we selected this one, we selected this one, and we selected this one, and the criterion for the classical design approach was this one. So in past classical design, we placed the current loop crossover frequency 20% of switching frequency. So you have different value of this. So these two are different from this. Okay, and this SE is 10 times larger than this. That means in here, this current mode control nature is very weak, and the voltage mode control nature is strong, which is opposite to this case. And this one, selecting this one is same as selecting QP in new design approach. Okay, if you perform the new design approach with this, you come up with exactly same value of this. Okay, so there are close relationship between classical design approach and the new design approach. Okay, comparison of loop gain characteristics. This is the new design. Okay, current new design is evaluate using new model, which include sampling effect, and classical model, which does not include sampling effect at all. Okay, so we are comparing this loop gain characteristic of previous buck converter. So switch the loop gain crossover frequency is this one, and the phase margin are the same. Okay, so in terms of the relative stability, they're exactly same, and this gain margin here is 20 dB, and okay, we are using the exact model here when evaluating gain margin. To have gain margin, the phase should fall below this minus 180 degree. In classical model, the gain margin cannot be defined here. Okay, but we are taking the phase characteristic of this new model, Dirichlet model, or experimental data, or computational method. Okay, so everything is the same except this peaking, small peaking, because this Q is one, peaking is very small, or peaking is not there, and this one is some numerical garbage generated by the PSIM program. But if they are very close, and this shows the new model is more accurate than the classical model. But if design is properly done in this manner, so difference here is this does not matter. Okay, because it occurs after switching frequency. Unless this peaking is very large, then it becomes unstable. Other than that case, this the classical model and the classical design approach is as good as the new design approach and the new model. Okay, that is the message from the previous lecture 11. So in this lecture 12, we want to discuss the details about this sameness in the two current loop design, new design, and the classical design. Okay, let me repeat this. So in the classical design, we select QP properly, and in classical design, we select this one, ratio between this current loop crossover frequency to switching frequency. Okay, so we found there is a relationship between this, and I already mentioned this several times. Okay, let me repeat this. This is the required condition to guarantee the identical current loop. Current loop becomes the same regardless of the choice of design method. I mean the new design and the classical design, if this is satisfied. Okay, as a specific example, let me show this. new design with QP as 1, okay, then you have this relationship. This is true. Assume this is true. We will prove this shortly. Then this should be true. And QP is 1. Then this is 1/2. Then this omega Ci is 0.5 omega S. Okay. So if you select this and perform the classical analysis, classical design, you have same result using this QP of 1 here. Okay? So there is one condition to have the same design, same current design in new design approach and the classical design approach. Okay? How about the voltage loop? Okay? Voltage loop, if omega CR is loop gain crossover frequency, is selected the same in two designs, then the voltage loop design is inherently identical in both new and classical design approach. Okay, so you need some requirement here. Okay, you should satisfy this, but in the voltage loop, if you select the omega CR at the same frequency, then everything remains the same. Okay, there is no reason to select this differently. Okay, so this omega CR is very important number. Okay, so you should select very carefully. Then there's no reason to select differently. Okay, so everything should be the same. All right. Okay, so I summarized the new and classical design procedure. So in the new design procedure, we include this HES is the S-domain representation of sampling effect of current mode control, and actually Didri developed this. Okay, this is the 0. It is in the numerator. The unique thing is the quality factor QG. G means 0 is negative number. This is RHP 00 occurring at the Hepto switching frequency. Okay, it does not mean system is unstable. Okay, to make system unstable, that RHP double pole should occur. This is 00. Okay, it really doesn't matter in terms of stability where it has RHP 00 or LHP 00. Okay, and classical design procedure does not incorporate the sampling effect at all, and somehow nonetheless the two design procedures are very similar, almost similar, except the current loop design criterion and the difference and the similarity of two design procedures are explored in this lecture. Okay. This is a comparison between the new design approach and the classical design approach. In new design approach, we attempt to provide a desired QP by selecting the compensation lamp wisely. Okay, so there is some value, predetermined value of the QP, and everything is determined. Then you select SE to satisfy, to make this QP for some value. Okay, if QP is 1, you make this thing unity. Okay, and in classical design, we tried to control this omega Ci ratio of omega Ci to omega S. Okay, omega S is this one, and omega Ci is this one. This is omega Ci. We went through this. Okay, and there are this Fm prime is coming. Okay, and Fm prime is the modulator gain of classical approach proposed by Fred C.D. and this is the expression of Fm prime. Here we have SE. Okay, so in this approach, we are selecting this wisely to have the desired ratio between this and this. Okay, so the criterion is different, but the way of achieving our target is the same, just selecting SE wisely. So there is an intimate relationship between two design approach, okay, because there is only one free variable, which is SE, right? So I claimed there is a relationship between this. There is a relationship between QP and omega CI, and that relationship is this one. This one, okay? Omega CI divided by omega S is exactly same as QP divided by S. If you select QP as 1, then that is the same as this ratio to be 0.5. We prove that. Okay. Initially, I didn't know this. I was not expecting this because apparently there are two different approaches, and one is including the sampling effect, and the modulator gain are different. This modulator gain and this modulator gain are different, and somehow, and this model is considering from the feed-forward gain from input voltage and the feed-forward gain from the out voltage, and this model does not include anything. So apparently, it's two different approach. So for the curiosity, I plot this. Okay, this x-axis is QP, and this y-axis is this one, omega CI divided by omega S. Okay, so this is the final result, and I select, for example, I select this point. Okay, and this QP is 0.8. Then I calculate SE that provide the QP of 0.8, okay, using this equation, and I evaluate this, and I used SE, this SE, providing this QP of 0.5, and I used that particular SE value here, and I put SE here. This is the ratio between omega CI, omega S. Okay, this is the omega CI, this is omega S. Then this number, this, so I used this SE, and I put that use SE here, and the result was 0.4. Okay, I repeat this here, everywhere, and I found that this is a straight line of slope of 1/2. Okay, very strange. Okay, I checked this again and again, and this is absolutely true. And then I switch from the buck converter to boost converter. I repeat same things, so I obtain this. Okay, this is the same curve. Okay, exactly same curve. Right. So this relationship is revealed from this graphical analysis. For example, the design of new design with QP 0.5 is same as this one. In classical design, the ratio becomes 0.25, and QP of 1 becomes the ratio of 0.5 exactly. Okay, so I tried to verify this. Okay, the verification was easy. Finding out this fact was accidental or not easy, not apparent to predict. Okay, derivation was very easy. So I tried to verify this. Okay, so my target was to derive this equation. Omega CI divided by omega S is QP divided by 2. So omega CI divided by omega S is this one. This is omega S, and this is omega CI. This is easy to evaluate. Okay, and I separate this. This is Fm prime, and this part is Fm prime. Okay, this is a classical model. So I'm talking about the classical design approach. All right, and I denote this as A and denote as B. So A is this one, KID Ri times omega naught squared omega ID. The KID is this one for the buck converter, and Ri is current sensing network gain, and this Powers double pole frequency is square root of this. So we squared. So you have this, and omega ID is this number. Then you have this cancellation, and this is the final result. Okay, so A becomes A prime. Okay, and this one B. B is the expression of modulator gain in classical model. This one, and I use this parameter. Did we define this? This is the same equation using this. Okay, and we have this. So this is the slope of sensed inductor current. This is the on-time inductor current. This is a current sensing network. So this is SN, EMs. This is SF. Same thing. This is buck converter. This declining ratio is VO divided by LTS. Okay, and this is the same expression rearranged using this MC. This same thing. Okay, then this A becomes A prime, B becomes B prime. So originally this omega Ci divided by omega S this is omega S, and we have A, B is FM, and it modified this here. Okay, this is the final result, and you have many cancellation with this. There are so many cancellation. Then remaining thing is this. Okay, this is the remaining expression, and MC is this one. This is the definition of the MC, and you put MC back into this expression. Then final result is this one. This one. 2 is here, and this part in this dashed line. This is what? This is QP. Okay, QP emerged here. Okay. We take the entirely different approach, but somehow QP is appearing here. The QP is defined. The needed approach. Okay, let's say. Then this QP, then this QP divided by 2. Right. So this proof is not very easy. Okay, but very mysterious. Okay, one include the sampling effect, and one does not include the sampling effect. How come they come up with the same result? Okay, probably the Fred-List model is somehow include the sampling effect. Okay, or did this model include the sampling effect, but their sampling effect is largely disappeared during the manipulation of this, probably. Okay. I don't know, maybe not true. The peaking is appearing only in Dietrich's model, and the Fred-List model is very peaceful. No peaking, whatever, but somehow the final result is ideally identical. Okay? All right, so this is about the sameness in current loop design, and how about the voltage loop design? Okay? New design, KB, is this one. And classical design, KB, is this one. Okay. There are selection of omega G and the selection of the omega CR. Okay. That remain the same. There is no reason whatsoever to select differently. Okay. You assume that they selected the same, and if the KB remain the same, then everything remains same. Okay, the feedback compensation, we are selecting the omega GC and the omega PC, they remain the same. Okay, and the KB will be different. KB will be different. Okay, so in new design, this is the equation for the KB, and this is the equation for KB in classical design. So they are the same, and I denoted this A, and this is B. Okay, and we will prove this A and B are the same, approximately same. So this is the A, and this is the B. They are very similar, almost same, practically the same. Okay, so we prove this. Okay, new design KVCI is given this one. So this is the R divided by Ri, and it has some debris. It is coming from the sampling effect of something. Okay. But this number is very small. This is very small compared to this one. We observed this. This is the 0.02, something like that. Can be ignored. then they are very similar or almost the same. And omega PL is given by this in due design. In classical design, omega PL is this one, and the KVCI this one. So you have some this debris, okay, in due design, but this is very small compared with this one. We prove this more than 1/20, okay, something like that, can be ignored. So because of this, all right, then this A is this one, and this B is this one, okay, then A and B the same, okay, practically the same. A and B are the same, practically. So everything remains the same, okay. So the current loop is the same if your design satisfies that equation, and the voltage loop is the same if you select the same loop gain crossover frequency, okay. So this is the final conclusion of this analysis, okay. So somehow this is very easy, okay, to follow, but I intend to visualize this, eliminate this, okay. So take the boost converter as example. So due design guideline is this one. Somehow I modify this, select QP some number between 0.2 and 1.2. Then this design guideline becomes the same as this. I obtained two limit, low limit and upper limit. Low limit is obtained by this number divided by 2, and upper limit is this number divided by 2, which is this. Okay? So suppose you determined to select QP of 1 in due design. This is 1. Then this divided by 2 becomes 0.5. Then you perform your design using this and follow the due design procedure. You will obtain this result. Okay? And you select this one, the ratio of 0.5, this one, and follow the classical design approach. You come up with this. Exactly same design, and this current loop design, you should satisfy this condition. And how about the voltage loop design? This is the guideline for the voltage loop design. Omega PC is here, and some number. Oh, this one. Omega PC, omega PG. I forgot to write down this. Omega GC was 0.8 omega naught. Okay, this is the same. All right. So then this is selected, and this is selected. Okay. So if you select this, KB is selected like this. Okay. So this is the same. This is the same. Okay. We observed this as long as this omega CR is selected the same, everything remains the same. Okay. So we have only one hardware design, hardware implementation. Whether you follow new design or a classical design, result should be the same. Okay. Because you followed this rule. So this is the performance of your design. So you select. We used this in the previous example. Okay. So you are using this again, and this is the experimental evaluation. This is the result of the computational method, but can be considered as a hardware experiment. Okay. There is only one this loop gain because there is only one hardware designed following the different procedure, but result is identically the same. And this is a crossover frequency, and this is a phase margin, and this is a gain margin here. Okay, because this is the 180 degree. So gain margin can be clearly designed from this hardware. Okay, gain margin is difference between 0 dB and gain of the current loop gain at this frequency, which is 12 dB, and this is the 500 hertz, and the phase margin is probably less than this. Okay, to be exact, I don't know. Okay. This is the boost converter. So this crossover frequency is narrower than the bulk case because the presence of the RHP0. Right? And empirical data. This is the measurement or computational method and audio susceptibility. Okay, this is a hardware measurement. There's only one hardware, so everything should be the same. And this is the step load response and the step input response. I simulate this using PC with the previous circuit model. Okay, so it can be considered as the hardware measurement, particularly the time domain simulation and the measurement is almost identical. Right? And from here, you observe this. This is this frequency. So there's one asymptote, another asymptote, another asymptote, and this is the peak value of output impedance. There is related with step load response, and we ran this several times, at least 2 times, probably more. So now you understand this. So there are 2 corner frequency. One is this, and this one is higher than this. Then we have 2 exponential terms. One is this red one, which is slow, and one is this blue, which is fast. Okay, and the coefficient of their different. This one is positive, this one is negative, and there is a peaking, this one, and also there is peaking. Okay, but at this, the magnitude of this and the magnitude of this are different. Okay, so difference between this slow peaking and this fast peaking is given by this, and this is the initial jump. Okay, so initial jump occurs here. So if you take close look at this, there is a jump here, and it follows difference between this curve, and it converges to this one and go like this. Okay. I told you this the magnitude of initial peaking is given by this is the ESR of capacitor, ESR times the step, jump of step, which is 4n, is this initial jump. Okay, here very small. Okay, VO jump, initial jump is given by I step times ESR of capacitor. Right. So this part is just this horizontal line of ESR. Okay, this is open loop output impedance, and this audio susceptibility is very similar to this, but difference is this will go down. Go down. I don't know what happened here. Okay, it shows what low pass filter characteristics at high frequencies. Loop gain becomes magnitude of loop gain becomes very small, and everything becomes open loop transfer function. And we have only 2 corner frequencies, and one is given by this, and another one is given by this. This one is slower, and this one is faster, and the sign is opposite, but the magnitude of this and this should be the same. So it starts from 0, it goes like this. There is no initial jump here because this value should go to the 0, because this is low pass filter, right? So there is no initial jump. Okay, so this is the measurement or experimental result using this prototype converter. Okay, and the difference is coming here. Okay, you have one hardware design, but we have 2 different models which does not include the sampling effect and which explicitly include the sampling effect. Okay, this is the new model. This is the leadless model. So this model has this KR and the KF, which is very small, relatively small, and the modulator gain of this model is this one. This one is very similar to the case of voltage mode control. If you see the proof of this looks okay, but during proving this, deriving this, he assumed this is 0, which is not true because this is connected to our voltage. This can be considered 0 because this input is grounded, but this output voltage is not grounded, so something is coming in, but he just ignored this and only he used very similar approach of the voltage mode control with some additional component, and he obtained this. Okay, so I have some doubt about his derivation. Okay, and this is not a sampling effect. This is the S-domain equivalent form of the sampling effect. I introduced this in the previous lecture. Okay, if you derive a transfer function of this from here to there, it becomes minus HES. Okay, exactly HES with minus sign, because this is an inverting amplifier. So we have minus sign inside of it, so there is a positive sign here. Okay, so actually this should be negative feedback. All the feedback should be the negative feedback. Okay, negative sign is inside of this circuit. Okay, so this is the small signal model of converter, including sampling effect. And this can be programmed using PSIM. Okay, PSIM. I don't know. Maybe PSIM takes this negative resistance. Okay. Otherwise, you need something else. All right. So this part remains the same. Okay. And in classical model, this is the Fredis model. So there's nothing in between. So you need the minus sign here. This is negative feedback, and this one is totally ignored. But this modulator gain is somehow different from this. Okay. So SF is coming here. There is no SF here. Okay, because he ignored this KR block. Okay. Okay. Anyway, this is a classical model, and the new model, and this is the simulation result. This this blue or black line, continuous line, is prediction of Didris model, and this one is Fredis model. Okay, and this thin line is measurement or computational method. So Didris model is more accurate. Okay, very accurate at this region. And in terms of the phase, this is the phase of measurement, and this is the phase of Fred C, this model, and this phase of Didris model. So Didris model is much better in here. Okay, but in terms of design, it really doesn't matter. Okay, actually you don't want to see this. Okay, you don't have to see this if you design the controller properly. Okay. One thing here. Okay. We use the same two different models, new model and classical model, and this output impedance and audio susceptibility for this boost converter remain the same. In the previous example, in lecture 11, when we use the buck converter, there is a huge difference in audio susceptibility. That is the result of reduced SE. Okay, strong nature of current mode control improve this audio susceptibility. But at that time, I told you that is the true only for the buck converter, because of the special structure of buck converter. In other converters, boost and buck converter, this one is the same, and audio susceptibility is the same. So both the output impedance and audio susceptibility are the same, and this reveals some problem of this new model. This is the prediction of the new model. It goes to the zero here. Okay, it doesn't make sense. Okay, this is not a switching frequency. Actually, this is the half the switching frequency. Why it goes to here to zero is the problem. And one problem with his model, HES model, is as a second order system, and the numerator, order of numerator is 2, order of denominator is 0. That is not feasible in practical system. Okay, in the older linear time invariant system, so small signal model is linear time invariant system. Okay, then order of numerator is larger than or equal to the order of order of denominator is larger than or equal to order of numerator. Okay, that's true. That is proved. Okay, so but this HES is order of numerator is 2 and order of denominator is not 1, 0. Okay, something unexplained. Okay, maybe because of that, some problem is occurring here. I don't know. Okay, that model is it has some flaw there. Okay, if you see the older gain blocks, the order of denominator is equal to or larger than order of numerator. One exception is HES. All right. Okay. Final remark. Initially, I wrote down here, but this is unnecessary. Okay, this maybe this you got confused with this. Okay, so this is the final statement. I modified somehow. Okay, either the classical design or new design can be used if the design guideline of this one, 0.1 to 0.6 for the classical design, or the same condition, QP, some number between 0.2 to 1.2. Okay, the same thing is employed. So you select any number of in between here and follow the classical design, and you select any number in between new design, then you have a good design. Okay. But if you select this one, you are designing converter twice, and you select omega Ci, omega S. This is necessary for the classical design, and QP is necessary for the new design. And somehow you selected this number to meet this condition, then there is only one design. Okay, that is the final statement. So the new design is not absolutely needed. Okay, it will provide some information, but classical design is as good as the new design. Okay, this is the final conclusion of this. Okay, so I think this is the summary of this lecture 12, and I hope you consider this as the final resolution to the column mode control. Okay. It's up to you, okay? But this is what I'm claiming, okay?